This is part 7 of a video series where you have projectile motion, but you're throwing the object up at an angle, as seen here, and it follows this path, which is called a parabola. It's the trajectory, called a trajectory, but the shape is a parabola. And what you're seeing is an arrow representing, right here you have an arrow in a second, it's coming back. The arrow represents the speed of the object. And so the speed overall, not breaking into its components, which we will have to do in this unit, is decreasing on the way up, increasing on the way down. And if you pass that initial point where it's level, it's going to be faster down here. It's, as you can see by the arrow, it gets bigger than it ever was in the first place after this point where you'd be at the horizon. So there's some key things to think about. We do have to break this projectile into some components when we have to do any sort of math on it. And so the initial, I'm going to draw an arrow over this, and I'll draw it again on the side. The initial velocity, let me just go ahead and let's make one up. Let's say it was going 20 meters per second and it was thrown at an angle of 35 degrees above the horizon. Now, just a note here, if you wanted to get the furthest down range, which is this way, you want to throw it at a 45-degree angle to the horizon. And if you want to get the highest, of course, you're just going to throw it directly up, which would be a 90-degree angle to the horizon. But let's say we have an angle to start off with. So this is how you start any of these questions where you have to solve for math, and then we have to look at some key components here. But the initial velocity was 20 meters per second at an angle of 35 degrees to the horizon. And so we're going to have to break that into its x and y components. Now with projectile motion, the x component, Vx, is going to be constant, whereas the y component going up is going to have acceleration of due to gravity, which would be 10 meters per second squared. In this case, we're going to go ahead and say down, and we'll probably say negative 10 meters per second squared, because the object's going to be going up in the first place, so there will be a positive velocity to start off with. And then depending on where it lands or where it goes, it's going to have a positive or negative velocity when you're calculating for something else. But the acceleration will always, this is always going to be the case, it's always going to be affected. It's in free fall. Once again, it's not that it's thrown, but that it's in the air, just of being affected downwards the whole time. A equals 10 meters per second squared downwards. So to start this problem off, we're going to have to break it into its components. So the way I worded this question, you're going 20 meters per second, that's the speed, and it's at a 35-degree angle to the horizon. So we're going to break it into its Vx component, and we're going to break into its Viy component, Viy. Because this is the initial velocity, which will be changing throughout the flight. To do this, across the way from 35 is the opposite, and to find this is going to be the adjacent. So to solve for Vx, we're going to use SOHCAHTOA, and adjacent ends up being the cosine of the angle times the hypotenuse, and the opposite equals the sine of the angle times the hypotenuse. And so here we have our initial y is going to be sine of 35 times 20. So our initial y component is going to be, and make sure your calculators are in degrees and not radians, which mine is. So sine of 35 equals times 20 equals, so the initial y component is going to be 11.47 meters per second here. And then the x component, so that's going to be Viy in our givens. For most problems, they could be worded funny where we might use it somewhere else. For our adjacent, for our x component, so Vx, which is equal to our adjacent, it's going to be cosine of 35 times that 20. So cosine of 35 equals 0.8 whatever times 20, and we get 16.38, or let's say 16.4 meters per second. So anywhere in this flight, the x component, Vx is unchanging. It's always going to be 16.4 meters per second. That will be the same no matter what. Often you'll see the line drawn like this and it won't change. Well, in this case, in the picture I drew, let's find out where this projectile is. There it is. There it is. This Vx anywhere, A, B, C, D, wherever, they're all going to be 16.4 meters per second, unchanging. And then let me go ahead and clear this up a little bit. So my Iy equals, and it was 11.47. So Vx, which we solved for in our last one, was 16.4. So these are going to be given in any sort of equation you have, and I'll give you some practice a little bit later on. So my VIY is 11.47. What that's saying is this right here, this initial component was 11.47 meters per second up, and my initial x is going to be 16.4 meters per second. This VIY, depending on if you're trying to kick a field goal or see how high up objects are going to be thrown, another given that you need to realize, if you're starting from this initial spot and I'm asked for, okay, how high is this object going to travel? Well, you need to realize one fact. If it's starting with a VIY of this, when you get to the highest point, your V final Y, in this case, the way I wrote it, once again, depending on how the question's worded, this might change, is 0. At the top of its flight, its velocity is in the y-axis is 0, and then it speeds back up afterwards. So this is a given. If you're trying to find how high, you're gonna have a given as VIY equals 11.47 meters per second. Vfy equals 0 meters per second. You have an acceleration of 10 meters per second squared down. In this case, we'll go ahead and call it negative because this was a positive. And then we would solve for x. And the equation we would go for in that case would be, we have Vf squared equals Vi squared plus 2ax. And so if we were solving for that, it would be 0 squared equals 11.47 squared plus 2 times negative 10 times x. And so when we were doing this, we would get 11.47 squared equals 131. Let me just round it to 6 plus negative 20x, which was really a minus 20, equals 0. And then the next step is we'd have to subtract both sides by 131.6 minus 131.6. And we'd get negative 20x, I'm just going to rewrite that on this side and this on that side, equals negative 131.6. And when you divide both sides by 20, you'd get 131.6 divided by 20. I took out the negatives because they're going to cancel each other out. So this ball will get to a total height of 6.58 meters. Now, in another problem, you might want to find out, well, how far downrange is this object going to travel? And here I used x, but often you'll see, once again, I just want to state, this a might be g, and to specialize, this x probably would be written as y. Just want to make sure I don't leave that alone. And so here, for dx, if we're trying to find how far it's going to travel, well, this would be a harder problem. Let's go ahead and stick to an easier problem for now. How far is it downrange when it gets to the same height? If that was the case, how far downrange is it going to get when it gets to the same height? Well, our VIY, which we solved for before, I forgot already what it was, VIY equals 11.47 meters per second. Our acceleration this whole time is 10 meters per second squared down. We'll go ahead and make that negative because this is positive. And then the other given that you'd have to go if you're trying to find how far downrange, once again, to this point right here, not to down here because this would be a harder problem. At this point, the V final Y would be equal to the opposite of what, once again, in these questions, it's the theoretical ideal conditions, no air resistance. So if I'm trying to find out how far this is gonna land downrange, what I'd have to do is I'd have to use the VIY, the A, the VFY to find the time it took to get to this point. And I have VF equals VI plus AT. I would use that equation. it would be negative 11.47 equals 11.47 plus negative 10 t, and we get negative, it would be negative 22.94 when I subtract out 11.47 from both sides, equals negative 10 t. And so when I solve for this, it would be, and once again I'm using 10 instead of 9.8, some of you might be using 9.8 right now, 2.294 seconds. And then if I want to find downrange, I would be looking at the x-axis now. So I just found out how long it's going to be in the air, how long it takes to go up and back down, and that's the time it's going to have to go at constant velocity this way. So the time it took was 2.294, and the whole time it was traveling with an x component of 16.4 meters per second. And if I wanted to find out how far our downrange, v equals x over t, we rearrange that, and this is just dx the way I wrote it here, and this is vx the way I wrote it here. dx, or just x, equals v times t. And in this case, it would be 16.4 times 2.94. 16.4 times 2.94 equals, and so this object would have landed 48.216 meters downrange. Once again, only to this point right here. I'll do in a future episode, or if you have any questions, just write a comment and I can do an additional problem that you might have. Thank you.